Hello everyone, my name is Benedikt Meurer. I work on the V8 team together with Michael and 28 other people. We are mostly based in Munich, as Michael already pointed out, and we basically built the JavaScript engine that sits underneath Chrome, Node.js and various things on Android and whatever other products you might know. My talk is about ESnext Performance, so specifically about why we would even care about ESnext, what ESnext is, and yeah, some nasty details that you might want to know or might not even want to know. You will figure out later. So I will start with the why. Why would you even care about ESnext? So when I talk about ESnext, I'm specifically referring to everything that happened after ES 2015. So the standard that was previously named ES6 and later renamed to ES 2015. So basically, you might know this thing from 2016. That was early 2016, a big survey among JavaScript developers all over the world. And the result was very interesting, especially the aspects about the language flavors. There were also results about frameworks and what frameworks would be interesting in the future, and that didn't really work out. But anyways, the prediction for the language flavors worked out pretty well. So specifically, there was this one question, which is about language flavors in the sense of plain old JavaScript, which is now known as ES5 or ES6 or TypeScript or whatever, CoffeeScript, ClojureScript, which didn't really materialize. And back then it was already visible that ES6, even though not many people have tried it, gained a lot of interest. So of those people who haven't tried it so far but heard about it, 90% said that they would be interested in learning more. And among those who tried it, the satisfaction rate was immense. They said that 98% of them were really satisfied and would do it again. So basically use that in the future. And it was already predicted that ES6 will become the default way to write JavaScript applications. And 2 years later, or 1.5 years later, we can see that this is the case. So I tried this experiment myself and tried to get more opinions on this. So I ran this on Twitter 2 months ago and asked people, hey, what do you use to write your application? Not what you ship to the user, but really what is the input language? What is the language that you use? And as you can see from the result, almost everyone is using modern JavaScript, either in the sense of using TypeScript, which has the features of the upcoming standards already, or ES 2015 and above. This is obviously biased. So first of all, there are only 2,800 votes, and this is biased towards people who follow me on Twitter, probably. So this is not representative of the world. One observation that not one observation, but one theory that we have is that the TypeScript is way more dominant in the corporate space, and those people are usually working in closed environments and traditional Microsoft environments, and their TypeScript is stronger. So maybe we need to add a couple of % to TypeScript. But that doesn't really matter, because TypeScript is also just ESnext in some sense. Okay, there was one interesting result, because if you look at it, then it seems a bit strange that you can develop large-scale applications using just ES 2015, which is arguably way better than old-style JavaScript, but it still makes refactoring more difficult, and it leaves errors in the code that could have been detected by TypeScript. And there were a couple of comments on this and follow-ups. I'm only highlighting 3 of them, because people who responded ES 2015 were actually not necessarily using that plain ES 2015, but using that with flow type, so Facebook's type system. So they do indeed use type checkers, just not TypeScript. Okay, so that's the motivation, why it even matters. Now the question is, what is this all about? So what is ESnext about in today's world? Well, if you look at it from a distance, then ES 2015 today means basically you need your tools. And the core tools here are Babel, Webpack, and TypeScript. Maybe a couple of others. But this is what you hear when you ask people. This is the first thing that people will respond. And there's also Node.js, which provides a native environment for ES6. So Node.js has the advantage that you can just target the specific Node version and thereby target the specific V8 version, and you know exactly which features are supported. Whereas if you ship an application on the web, you probably need to deal with old Safari versions, old Chrome versions, or even versions of Chrome or versions of Chromium inside of Samsung Internet Browser or whatever other browser. So you don't really know, you don't have a dedicated set of features that you can use that are not necessarily ES5. Okay, so this is the world we see today. And there's a new world or an additional world that we are entering, which is we get native ES6 environments or even ES 2017 environments on the web as well. So all the major browsers caught up. The basic support for all the features is there, at least for all the ES6 features, excluding modules, which is a story of its own. But even that is coming. So we have the fundamental compatibility across all the browsers, not only Node, we can also rely on modern browsers to support it. And there's one thing that is now interesting, which is performance considerations. So your app not only needs to start without throwing undefined is not a function or something, but it also has to start reasonably fast. So this is the area that is being worked on currently and probably one of the main blockers still. So if you look at it from a engine's point of view, then what we see today is we have two worlds when it comes to ESnext. There's one world, which is the generated ES3, ES5 code, depending on what tools you use. And this is usually the output of some transpiler, so either TypeScript or Babel or Traceur or any of these tools. So it's generated code. It's not the code that you write, but the code that the tool generates for the code that you wrote. And most importantly, this is usually bundled. So what we see is not modular code, which contains various modules, but we see one or two big bundles of JavaScript that contain everything. Nowadays, not only JavaScript, but even CSS or other resources are also included in the JavaScript. And the other world is the native ES 2015 and beyond world, which is what we are working towards. This is already kind of what's going on in NodeSpace, but not yet what's going on widely on the web. And in this world, the code is usually handwritten, because it's the code that the programmer wrote, and not the code that the tool generated out of this. Usually handwritten, because there's also minification and uglification and whatnot going on. But in theory, it's the code that you wrote. And it will be modular, or we expect it to be modular. We don't expect these large monolithic bundles anymore in the future, but we expect a future where really you ship your individual bundles to the browser. Not necessarily without doing anything, because that wouldn't scale for large websites that have 800 or 8,000 bundles, 8,000 modules. That wouldn't scale, that would completely kill the browser. But also not this monolithic approach that we currently have. Okay, so let me show you a simple example to motivate what we'll be talking about today. So here you see two classes, class A and class B. Class B extends A. So it's a subclass of A, and both have a function foo, and the function foo and the subclass just calls the superclass foo and adds 1. So this is not really exciting code, and granted this is really artificial example, but let's just run this simple example through Babel and see what we get out of it. So Babel generates multiple parts here. To fit this on the slide, I had to minify it and use a smaller font. You already see where this is going, I guess. This is the code for A and B. But this is not all. We also need this support code. Just generated by Babel, plus bubbly for minification. Nothing added, no bundler, no other overhead. It's exactly the code. If you run it through Babel, this is what you get out of it. Yeah, without further digging into what it is doing, I'm coming back to this later. Here are the plain numbers. So you inserted 66 characters, unminified, and Babel successfully turned this into 150 characters, 1,500 characters. So even if you have the best gzip algorithm, you will still pay for this. And you not only pay for shipping this over the wire, you also pay for parsing this. So just on a high level, if our parser sees the left-hand side, even if it's doesn't really know how to handle classes well, it's probably still faster to parse that than all the stuff on the right-hand side. Sorry?
That's ES3. This one is ES3, yeah?
No, this is actually ES5. So this is default Babel configuration. It's the default Babel. So okay, so so I upgraded. Okay, let's use this less back compliant mode of Babel. So Babel by default tries to be mostly compliant with the JavaScript specification, which makes a lot of sense, but also leads to a lot of unnecessary code. So okay, there's this loose mode. So let's try that. That should generate a lot less code. And indeed, the code is a bit shorter, and also the additional code is shorter. But still, it's more than a factor of 13 increase in in number of characters, despite the minification. And okay, so this was classes. Maybe we try something else. Maybe we're just holding it wrong. So let me try something more exciting. This is a pretty simple async function that contains a for-off loop that awaits on that iterates over an array of promises, and we just await the promises one after the other. Okay. So let's look at what Babel does for this. Default configuration, nothing fancy. Sorry. Okay, this is the function itself. So your one-liner or two-liner turns into this monster. Obviously, there is some support function that is needed, which can be shared depending on how you bundle it. And yeah, for good measure, this also needs the regenerator runtime, and usually ships with a Bluebird.js promise implementation, just in case the browser doesn't provide native promises, or because people want to use Bluebird for better performance. If you add up everything, then that's just depressing. So that's basically what happens today, and that's what we see as ESnext performance problems. We have to somehow find a way to make all this garbage that is created by the transpilers fast, and this is a problem. But before I give you some details on the VM side, let me just show you one statistic that is really alarming. You might have seen this before. This is statistics from the HTTP archive. And there is a trend in there that is unfortunately ongoing. So we did a blog post 2 months ago, and there we reported that the average website contains 410 kilobytes of JavaScript. And since then it already gained another 16 kilobytes on average. So the problem is, if you continue this trend, that is exactly opposite to what the user base is doing. So users are more and more consuming the web via mobile devices. So the more JavaScript is being shipped to the browser, the less exciting the overall experience will become in the end, because it just takes time, not only to transmit it over the wire, but also to load it and parse it and evaluate it. So I did a small experiment, not really representative, but maybe there's something to gain from that. So I tried with 2 small examples of websites and see what is the estimated overhead of transpilation. Oops. Too much JavaScript. Good point. Okay. Okay. I don't know what that was. Maybe it was JavaScript, yeah. Okay, so I did this small experiment and just measured the impact of transpilation. This is not really a representative experiment because there are multiple issues. So first of all, the minifiers for ES6 code are not on par with the minifiers that we currently have for ES5. So Babeli is, the community somehow settled on Babeli, but it's not on par with what Uglify.js or other minifiers can do for ES5 code. So ES6 code can probably still get a lot smaller over time as these tools improve. And also I just took random quick start examples, so that's also not really representative of websites. But I measured that the overhead, despite all these shortcomings, is up to 30%. Which means if you take that back to the data that we saw on the previous slide, that means the average website could be less than 300 kilobytes again, which would be a really nice drop if we can get there. And the parsing cost would go down significantly. Okay, so you probably have seen Sam talking about this sometimes. He's talking about this all the time, actually. This is also the pastime. It's not only what you transmit over the wire, which is wasted bandwidth for the user. It's also what we feed into the parser. And pastime is startup time of your application. And pastime is really, really an important factor. So parsing just 1 megabyte of JavaScript almost takes 2 seconds on a Nexus 4. On a Nexus 5. And that's not even emerging market device. This is Western world device. So yeah, anything that can help us to reduce parsing cost, and just applying my number, my estimate would allow us to reduce the parsing cost to 1.2 seconds already, or 1.3 seconds, which is pretty significant savings from 1.8 seconds, in theory. Okay, so you usually get this advice from many Chrome engineers. If you watch talks or if you attend conferences, then it's like, ship less JavaScript and the world will be a better place. I guess it's probably not very useful to hear this over and over again, despite being true. So there's another advice that I could give you. You can just transpile less. And the way why this would work is the browser support it now. And we are almost there with the performance. So just the time you save parsing and shipping your data should already oftentimes account for the time that you might lose during execution, because it's not optimized to the maximum yet in all the browsers. This advice is not really innovative, but maybe I can convince you with the rest of the talk that you should still do it. So the question is, how can you get there? First of all, gain some trust. Browsers do support it. There's this Kangax table, which was done by Facebook and is now maintained by all the browser vendors. So the Kangax table states explicitly which features are supported in which browser. So you don't need to guess, or you don't need to rely on unreliable data, because this is up to date always. You can, for each feature you can check, is it supported in this browser and which version. For example, for Chrome, we have a fixed release cycle. Every 6 weeks there's a new Chrome version, and whatever was there before is basically dead. So we don't support old Chrome versions officially. That doesn't necessarily help because there are other vendors that still ship old Chrome versions. But even for them, so like for a Samsung browser, you can check the Chromium version that's built in and look it up. And obviously, support in Node is easier because it's monolithic because it's only built on V8, so you only depend on a certain V8 version. But there's also Node.green, which gives you the table of what's supported in Node. Figuring this out is tedious, so there's support. You can, for example, in Babel, there's this new cool plugin since last year, Babel preset.inf, that allows you to specify exactly which browser versions you want to support, and Babel figures out everything it needs, so it determines the right set of plugins. And in this example, which I stole from their website, it just says the last 2 versions of all browsers, except for Safari, they also want to support this ancient one. And then you get the proper code out. Specifically, if you're building something for an intranet or something that is not shipped to old devices, consider not using the default for all the frameworks or for web applications, but consider shipping new features instead. For Ember, there's good news. So Stefan Penner is currently working on making ES 2015 output the default, which is already possible for everything except Ember Core, but that will also happen soon. And related to that, because Ember often is, or parts of Ember are written in TypeScript, TypeScript also supports different outputs. Funnily, the default for TypeScript is ES3. I don't know why. This was puzzling when I discovered this, but you can switch to a newer target. The most interesting target is the ESnext target, but that's probably not interesting for shipping. ESnext is basically removing type annotations and turning a bit of the syntax that is not compatible yet into the JavaScript syntax, but it almost does nothing. That's the idea. Okay, so I promised some internals on the VM. So if you don't take anything away from the talk today except one thing, then take this away. Optimization in JavaScript is not homogeneous as you might expect, or as it might be obvious, but in fact it's not. All JavaScript VMs always optimize patterns. So pattern is something that you discover at execution time often. So there can be syntactic patterns, but most of the patterns are a combination of syntax and specific execution behavior or specific things we see at runtime. And this is true for most of the dynamic languages, because dynamically typed languages, you cannot infer anything until you execute it, because you don't know what's coming in. The problem with this pattern approach, or the good thing about this pattern approach is it turns dynamic languages into really fast and usable languages. So not only for JavaScript, but the same exists for Python and Ruby and Dart and yeah, whatnot. But the number of patterns is always limited, and each individual pattern comes at a cost. So there's no free lunch. Let's look at how this patterns, what are traditional patterns. This is a very simple pattern. Type of strict equals something. All VMs recognize this and turn this into something more efficient than determining the type of and then comparing the string to something else. There's this very important pattern, which is probably the core for JavaScript speed, when you have a property access, either loading or storing, and O always has the same shape, whatever shape means at runtime, then the VMs turn this into really efficient code, so usually just 1 or 2 machine instructions. Then another pattern that is important, a method call, where let's say the foo is always on the same prototype, So in JavaScript, methods are usually inside on the prototype. So if foo is always on the same prototype, then you optimize this and you can even inline the function foo. Or another very important pattern, array access. If you're always accessing elements of an array. So elements in JavaScript mean it's in uint 32 range. Okay. Obviously there's a gotcha. The patterns are not necessarily the same. The ones that are listed are supported by all VMs, but there are patterns that V8 optimize, but JavaScript core, which is the foundation, which is the JavaScript engine in Safari, doesn't, and the other way around. So it's like sometimes people are excited to discover patterns, but then are frustrated because the pattern only works in V8 or the next version of V8 breaks it. So don't trust these patterns in general. Interestingly, now the interesting part, what are the ES 2015 patterns? So there was this code snippet that I showed for classes. And now let's limit it a bit and only look at the super call. So super.foo and parentheses. The relevant Babel code for that is the one above, and below is the generic part that is needed to support it. So extracting this a bit, we turn super.foo call into underscore get, pass some prototype magic in, and then call it. And if you look at underscore get, that's basically the property lookup from the JavaScript specification encoded as JavaScript. So what Babel does here is, instead of relying on the VM to do it, they basically program or they produce code that implements the JavaScript specification. The reason that they have to do it is because super calls are special, because super property lookups are special, because for the lookup you look it up in the prototype chain, but if you hit a getter, then you don't pass the prototype, but you pass the original receiver, which is pretty fancy, and that's why they need a special get function if they want to be half spec compliant at least. They are still not spec compliant. The problem here is, just by looking at it, it's pretty clear that the left-hand side is easy to recognize for the VM. The VM is like, yeah, okay, I know. They try to call foo on some of my parent classes. Whereas looking at the right-hand side, the VM has really no idea what you're doing. And it would take a monster pattern to recognize this at runtime and make this fast. So the takeaway from this is using Babel is awesome, because then you can use new features before the VM support it, and even ship your application to older devices. But this is not a long-term solution, because you can never reach the same level of speed. There was another interesting pattern that I discovered recently that was missing. So looking at this simple example, I was pretty sure that I hit this 2 weeks ago. I was pretty sure we produced the best code ever on this. And then I looked closer and I figured out that this is 35% slower than the naive ES5 version using function prototype apply and arguments object. And the weird part here was, we had all the functionality in the VM. This code does exactly the same, modulo details. And we had all the support in the VM that we needed. But our pattern was too specific to the second case. So I had to edit, and now the performance is the same as I would expect and everyone else writing this code would expect. And the funny thing is, this is a lot of what we are doing as our daily work. You find something that is not properly supported, but you have something similar already, so you need to extend the fast path, or you need to broaden the pattern. But patterns are not always good. Patterns can also work against you easily and backfire in ways that you don't want them to backfire. So there was a bug report last week on Uglify.js that made us look into this particular example, which is really surprising. So if you look at this code, then it's exactly the same code, except for the import of the Babel polyfill. But the performance is really different. So this code runs on my MacBook in 170 milliseconds, and this takes 800 milliseconds. Identical code, you didn't change anything except the import. And the reason is, after digging in a lot, that the Babel polyfill changes the string prototype. And we use the string prototype to protect certain optimizations. So just this simple example already shows the performance difference. These patterns are, we thought, okay, replace can be fast if we can avoid certain checks. So the specification for replace is really complex. I think it's like alone 10 pages just for string prototype replace. Probably even more, because it also involves some regex stuff. So it's really complex. But if you look at it for long enough, then okay, in the common case, if the array prototype is not changed, then we can be really fast and we can skip half of the checks. Okay, too bad if you then modify it. And even worse, if you weren't the one who modified it, but you just use some polyfill. So Babel polyfill is the usual polyfill that you would use, I guess. At least that's what you get for Babel, with Babel for free. So this pattern of, hey, nice, the string prototype is unmodified, we can be fast, works, but might not apply. So we need to relax this pattern a bit and check for more specific things instead of just checking that the whole prototype is unmodified. And yeah, this blew up in Uglify.js. Actually, Uglify.js triggered a bug in the slow case, and we were completely puzzled how they hit the slow case. And my colleague Jakob Gruber wrote a nice blog post about how this affects regex. So if you want to know more about this, I suggest you read this one. I will make the slides available later. Okay, so now back on the ES 2015 performance. How is it going? We used in the past, or we started 6 months ago, we used this tool or this benchmark called 6-Speed, which was done by Kevin Decker initially, and which just compares ES6 code to the naive ES5 code or to Babel, TypeScript or Traceur compiled ES5 code. After looking at it for some time, we decided that it's not really important to measure against the transpilers, because just trying to make the naive version as fast as the ES6 version was already significant. And so we reduced it to that and added a couple of interesting tests, and then ran after it until everything was green, or mostly green. Green means that the slowdown of the ES6 version compared to the ES5 version, the naive ES5 version, that is not necessarily semantically equivalent, but observably equivalent, that the slowdown is below 2x, so that you can use it without running into some weird performance cliff. And today we are mostly green, and other browsers are catching up too. So I'm not showing other browsers here. I don't want to blame anyone, but trust me, they are almost there, or you can figure it out yourself. And we made impressive improvements since M55, which was released in October last year, and now we are almost branching for M60, Chrome M60, and we are on average we are below 1.4x slowdown, and in the median of all these benchmarks we are close to 1x or 1.x. So basically ES6 performance is roughly on par now with respect to this micro benchmarks. The problem with the further performance investigations is we don't know yet how to continue from here, because there is no really meaningful ES 2015 benchmark that would cover a lot of the use cases. There's also no real use cases, so we have some vendors who want to build their websites with ES6 and ship them, Also not only build them, but also ship them. Some bigger vendors. But so far, only small vendors have done this. And the only benchmark that we have on the web that includes ES 2015 is the new version of Speedometer benchmark, which contains a tiny ES 2015 benchmark, but not really useful workload. Ideally, we would track real-world performance on the real web, but that means someone has to do it first. What we track in the meantime is we track the performance of Uglify.js, which is written in some ES6 and Webpack and Babel, and we try to improve that. If you haven't done it already, what would be nice for us is if you take the language survey that we sent out 1 month ago or 2 months ago already, where we ask 5 very specific questions about what you want to use from JavaScript and what kind of problems you run into, so that we can do better planning for next year. Conclusions from this talk. This is the most important thing. Remember this. We always optimize only patterns, and patterns might backfire depending on how they implement it. The transpilers, polyfills, like Babel polyfill, can accidentally work against the optimization patterns. So use them carefully, or at least don't trust them blindly always. ES 2015 performance is almost on par. And yeah, try to transpile us. That will make the web a better place. And that's it for me.